Welcome back, everybody, for the fourth lecture by Tom Hutchcroft. Okay, so over to you, Tom.
Great. Thanks, everyone, for sticking it out to the end. Today is going to be pretty disjoint from yesterday, although draw more on the first two lectures. So if you didn't follow everything yesterday, then don't worry, because this is quite separate. So what I want to do today is explain some of the main ideas, at least, in the proof that there is always a non-uniqueness phase on hyperbolic graphs. And in fact, what we'll really prove is that PC is always less than P22 on transitive chronal hyperbolic, non-amenable transitive chronal hyperbolic graphs. So just to recall some stuff we already discussed. So we have this kind of operator theoretic approach to percolation, which is a fancy name for a simple thing. It just means we're going to think of these connection probabilities as a matrix, TP. And again, we define P22 to be the value of P where this matrix becomes unbounded. Right? And we saw that in a transitive graph, that's always bounded by PU, the uniqueness threshold. So we discussed this conjecture that in transitive non-amenable graphs, PC should always be strictly less than P22. And we saw how, if you have PC less than P22, then it follows in particular that you have PC less than PU, which is the Benjamini Schramm conjecture. And also you have that the triangle condition holds at PC, so that you get all this mean field critical behavior and all that. Maybe just to briefly mention before we go further as well, another nice thing about this is actually if you prove PC less than P22, this is really just a very strong thing, and there's a number of things you can prove using this that we don't know how to prove. For example, just using the triangle condition. So there are some exponents that you can compute under this condition that we don't know how to compute otherwise. Okay, but anyway, our goal today is basically going to be sketching proof of this for lattices in hyperbolic space, basically. Just remember another thing that we did before. We had this kind of sprinkling lemma where we said, if you want to, you can always bound the effect of increasing P a bit on these two-point matrices by using this kind of geometric sum where this means an entry-wise inequality. Right, where again, this is the thing where you kind of explore the cluster of the origin at P, and then some epsilon density of new edges open up, and you go across them, and then you explore their clusters of P, and so on. You get this infinite sum here. Okay, and remember what we saw is that this implies, in particular, that first of all, the set of P where this L2 operator norm is finite is an open set. So this norm has to actually be infinite at P22. But in fact, it tells you more than that. It says if you're epsilon below P22, then this norm has to be at least 1 over epsilon times some appropriateness. So this is going to be useful for us because if we want to prove this conjecture for some graph, right, it seems a priori like we have to prove that the critical two-point matrix is bounded as an operation on L2. But this lemma says you don't really need to prove that. It just suffices to prove that if you look at the two-point matrix slightly below PC, if you just prove that that norm is blowing up slower than 1 over epsilon, then in fact by this lemma it's not really blowing up and you're done. So this buys us a kind of extra epsilon of room that we can try and show this slow blow up instead of directly showing that the norm of PC is finite. Okay. Now, this thing here, that the sufficient condition suggests the following strategy to prove the conjecture. Okay, for some specific graph set. Okay, so what we want to do is there are two steps. So the first step in this strategy, I should say both these steps are potentially difficult in general, but they're things that seem probably like they should be true, and indeed this is the strategy that will follow in the hyperbolic case. So the first step, we're going to look at the susceptibility, right, chi p, which remember is the expected size of the cluster at the origin. It's equivalent to the L1 operator norm of this matrix, right? It's the row sum. Okay, so the step one will be to prove that the susceptibility blows up exactly like 1 over epsilon as we approach PC from below. Remember, we saw that this lower bound just always holds for essentially the same reason as this lower bound. The matching upper bound is part of what's called mean field critical behavior, right? So for a general graph, we expect this to blow up. That's power of epsilon. And this power should be 1 in this high dimensional mean field regime. Okay, so of course, we don't know how to prove that every non-amenable graph has mean field exponents, right? As we saw, the best thing we know how to do at the moment is just to show some parallel bands. But nevertheless, we strongly believe that this should be true, that you should have this mean field in the non-amenable case. So at least this step is heuristically ought to be true. Okay. And then the second step, if you can do this one, then well, you want to show that this norm, the L2 norm, is little over 1 over epsilon. Okay, and suppose we've already implemented step A, we've shown that the L1 norm is big over 1 over epsilon. Okay, so if you have that, then to prove this, it suffices to look at this normalized matrix where you take the matrix, you divide by its L1 norm, and you look at the L2 norm of that, and you just need to show that this goes to 0 as you go to PC, right? Because you know the actual L2 norm that you're interested in is just the product of this L1 norm and this L2 norm, the normalized term. So if this is going to 0 and this is bigger over 1 over epsilon than the whole, then the product must be little over 1 over epsilon, and you're done. Okay. Now, the nice thing about this, well, I mean, so this matrix, the problem with it is it's a pretty complicated thing to say anything about. Taking this matrix of connection probabilities, dividing by the row sum, it's a tricky object. We don't really know very much about it. But one nice thing that we do have, just trivially, is that this matrix, the normalized one, is a symmetric bistochastic matrix, right? In other words, it's symmetric. That's it's obvious that if you change the coordinates, you don't change the. If you flip the order of the coordinates, you don't change the value. But it's also bistochastic just because we've taken a matrix and we've divided through, taken a non-negative matrix and we've divided through by the row sums, which are equal to column sums. So bistochastic just means all the rows and all the column sums are 1, right? So in other words, this can be interpreted as the transition matrix of some kind of random walk. Okay, and now it's kind of a complicated random walk. So one way of thinking about what it's doing in terms of the percolation is that at each step of this random walk, you're sampling a size-biased copy of the percolation cluster, the vertex that you are, independently of everything you've done before, and then jumping to a uniform random point within that cluster. Okay, so you can, it's not hard to convince yourself, we won't actually use this, that description is equivalent to this matrix here. Okay. So this is, not an unreasonable thing to look at, but it does seem like it might be hard to prove things about. On the other hand, this thing that we want to prove for step B is at least plausible. And so the reason is that, well, as P goes to PC, this matrix where you're dividing through, where you're normalizing by the susceptibility, is really spread out in the sense that you're taking this, the numerator here is a matrix with entries bounded by 1, between 0 and 1, and then you're dividing through by a huge denominator, right? So it becomes very spread out in the sense that it puts very little mass on any particular pair of vertices, right? TPUV is very small. The maximum of that is very small. Okay, and if you think about random walks on non-amenable groups with these very spread out matrices, generically they will have small norm, right? So of course the easiest way to, or the most obvious way to generate spread out random walks is just to take powers of a fixed random walk. And obviously that works by distance theorem, but if you take whatever random walk you like on your non-amenable transitive graph and you take it to the power k, right? So this will give you some very spread out walk. Well, its norm is just going to be the kth power of the norm of the random walk you started with. And this norm is less than 1, so this goes to 0 as k goes to infinity. And there are many other things you can think of, like if you take a uniform point on a ball or something like that, things like this will also work in that they'll have small. However, it's not true that every spread out random walk matrix on a non-amenable group or a non-amenable graph, not every such thing is going to have small norm. So, for example, if you think about the Kähler graph of the free group, right? So 4 regular tree, and you can think of the free group on 2 generators, right? You could have a random walk which is very spread out, but only because it likes to take big jumps on like 1 copy of the integers. Right? So let's say, it's randomly jump to a power of the generator A, where this power can take loads of values and it's uniform, or you multiply by the generator B, right, with some low probability, something like that. So it's very spread out. It's very unlikely to jump to any particular site, but it's almost always walking within 1 copy of the integers. Then in this case, it's because it's putting most of its mass on this like amenable subgroup, it's not going to have norm going to 0. In fact, it's going to have norm going to 1, right? Which is really bad. So, nevertheless, I mean, we would think that there's no reason for percolation to do something like this. So it's still something that's plausible that things should work out and the step B should work, which lends heuristic support to the conjecture being true in general. Okay. And what I'll be describing in the rest of today's talk is how we can rule out these obstacles in the hyperbolic case. Yeah. Good. And maybe to give you a rough summary of how it's going to work. Very roughly, and this takes some interpretation to make it precise, we kind of show that in the hyperbolic case, this kind of thing is the only obstruction to having small norms. So if you have a very spread out matrix on a hyperbolic group, then the only way for it to have small norm is for it to, for it not to have small norm, is for it to put a lot of its mass in the vicinity of a single geodesic. Okay? Which is something it can clearly do to not have small norm, but it turns out in the hyperbolic case, that's kind of the only way to not get small norm. Okay? And back to this. And of course, even once you prove that, you still have to prove that percolation doesn't put most of its mass on the vicinity of a single geodesic, which is actually still difficult to do. So it gives you something to aim for. Okay, so this is the theorem I want to sketch some parts of the proof of for you today. So I already mentioned this earlier, but just to state it again, it says that if G is a transitive, non-amenable Gromov hyperbolic graph, then PC is less than P22. And just a remark here is that Gromov hyperbolicity, which I'm going to define for you in a second, is actually, it almost implies non-amenability. This is almost a redundant condition, except that you have, well, first of all, every finite graph is Gromov hyperbolic for kind of stupid reasons. And also the integers and things that look like the integers are Gromov hyperbolic. But if you have any infinite transitive Gromov hyperbolic graph, which is not, which has superlinear volume growth, say, then it does have to be non-amenable. So what's the definition of Gromov hyperbolicity? So Gromov hyperbolicity, which, by the way, in geometric group theory, it's normally called word hyperbolicity. Of course, we don't have words if we're not doing groups, so it doesn't really make sense to call it that. But it was a notion introduced by Gromov, and of course, and it's sort of a coarse version of negative curvature in some sense. And one way of defining it, which is not Gromov's original definition, but it's due to Rips, which is called the Rips thin triangle condition, says that, and of course, and this is something that makes sense for any geodesic, but let's just do it for graphs. There's Gromov hyperbolic if there exists a constant delta, which, although it's traditionally denoted by delta, you should typically think of this as being a large constant, such that if you take any geodesic triangle, so you take 3 points and any 3 geodesics connecting them, then each side of the triangles should be contained in the delta neighborhood of the other 2 sides. So, for example, in this picture here, I have this side here, and it's contained in this neighborhood of the other 2 sides. Okay. Right, and you want to have one constant delta that works for all geodesic triangles. Okay, so what this is saying is that triangles look kind of like tripods, like they have this pinched shape where they come towards, they meet in some kind of central point and then diverge off to the 3 corners. So, so one example is trees. Trees are always Gromov hyperbolic, and indeed they're Gromov hyperbolic with constant delta equals 0. Right? Because in a tree, a geodesic triangle is literally a tripod. Right? So the 3 sides of this triangle go like this, and like this, and each side will just be contained at the union of the other 2 sides. No need to take neighbors. Just so you understand the notion, of course, R1, so one-dimensional Euclidean space, is hyperbolic because, well, essentially because it's a tree. So again, it's hyperbolic with constant delta equals 0. But of course, if you go to higher dimensions, RD is not Gromov hyperbolic anymore. You know, you can easily see if you fix any delta and then you take a large enough triangle, clearly each side is not going to be contained in the union of the other 2 sides. And again, it turns out that for transitive things, of course, everything finite is Gromov hyperbolic because you can just take the constant delta to be really large. So this is just trivial. But in the infinite world, everything that's transitive and Gromov hyperbolic is either non-amenable or it looks like the line. Okay. Now, of course, the one of the most important examples of a Gromov hyperbolic metric space is standard hyperbolic space, d-dimensional hyperbolic space. So let me just remind you what that is briefly, and hopefully this is something you have some familiarity with, but let me try and build up a bit more geometric intuition for what hyperbolic space is. So one way of constructing a hyperbolic space, you start with an open d-dimensional ball, okay? And then you change the metric on it roughly so that if you have a small line segment, a very small line segment that's near the boundary, so it's epsilon away from the boundary, then its length is going to be roughly its Euclidean length divided by epsilon. So the closer you get to the boundary, you're scaling up all the distances. And of course, you can turn this into a Riemannian metric and all that stuff if you want. Okay, but this is the main thing to keep in mind most of the time. So there are some standard discrete models, so graphs that have roughly the same geometry as d-dimensional hyperbolic space, which can be nice to keep in mind if you're more of a discrete person, you prefer to think of things like that. So, of course, there are many lattices in hyperbolic space as well, but for many purposes, the easiest model of hyperbolic space to think about is this one. So this is in 2 dimensions. This discrete model has the disadvantage that it's not transitive, although it's in a kind of very mild way somehow. So what you do is you start with a binary tree that you draw this way, so it has a distinguished end that's going off up the page to infinity, and then I've only drawn it to finitely many levels, obviously, but it has the things going down forever as well. Right, you draw it in the plane, and then you just draw straight lines through each generation, so you connect up neighbors, right? And of course, sometimes these ones you add the horizontal connections between are actually really far away from each other in the tree, right? Like these 2 vertices here, you have to go all the way up here and back down to connect them to each other in the tree. Okay, so this defines a graph, and this graph is rough isometric to the hyperbolic plane. So you can map this into the hyperbolic plane so that distances preserved up to constants, and everything's constantly subjective and so on. So it's really a nice discrete model of the hyperbolic plane that you might like to keep in mind if thinking about hyperbolic spaces in UCU. You can do a very similar construction in higher dimensional hyperbolic spaces as well, although it tests my ability to draw a picture. As you can see, this came out a bit of a mess where, let's say you want a graphical model of 3-dimensional hyperbolic space. And what you can do is you have a 5 regular tree, so 4 array tree, right? And again, it's drawn so that, you have a distinguished end, which is going up vertically, right? And you associate a box to each vertex. Maybe I'll try and draw it there and see if it comes out any less horribly. Right? Each vertex has a kind of dyadic box associated to it, and then its children in the tree have these kind of children dyadic boxes that are half the size below it. Right, and so on, and then you have the children below here, and blah blah blah. So if you kind of decompose the upper half space into these stacked dyadic boxes, and then you have the adjacency relation on these boxes, right? Then you get something which is a nice discrete model for 3-dimensional hyperbolic space or whatever dimension you like. So again, the annoying thing about this graph is that it's actually not transitive. But it's very close to being transitive somehow, and for me, it's the easiest to think about the discrete model for hyperbolic space to understand the geometry. Okay, but this is just to help you get some intuition for what hyperbolic space is sort of like. Now, so of course, as you would expect, these classical hyperbolic spaces are formal hyperbolic. And one way we can produce Gromov hyperbolic graphs is to have graphs that look like standard hyperbolic space. So these ones I've just been explaining to you how to construct, for example, or you might have calculations of the space or whatever. But it turns out that there are many other sources of these Gromov hyperbolic graphs as well. So in particular, hyperbolic groups, i.e. groups whose Cayley graphs are Gromov hyperbolic, arise all over the place. I mean, this is a really important notion in geometric group theory. So just to give you an example of a group which is Gromov hyperbolic but doesn't obviously have anything to do at all with standard hyperbolic space. So it's a theorem of Gromov that if you look at a random group in some sense, then it will be Gromov hyperbolic with high probability. For example, if you fix some generators and then you take a random set of relators where you include each relator of some big length independently at random with some probability that's small enough so that this group doesn't degenerate into the trivial group, then what you get will be a non-amenable hyperbolic group. Now, the nice thing though is, even though we can produce lots of examples of Gromov hyperbolic graphs and groups that don't obviously have really anything to do with standard hyperbolic space, it turns out we can always embed any Gromov hyperbolic graph inside a standard hyperbolic space in a fairly nice way. Okay, so this is a theorem of Bonk and Schramm. It says that if you have any bounded degree Gromov hyperbolic graph, then we can take a convex subset gamma of a Gromov hyperbolic space. So of course, convex just means that you have 2 points in gamma and they're geodesic belongs to gamma as well. And a function from the vertex set into gamma, so which basically says that geometrically the graph and the set gamma are kind of the same metric space up to some kind of bounded additive distortion, right? So more precisely, you do have to perhaps scale the graph up by a constant first. So you get that there exists a constant lambda in C, so that if you take distances between two vertices of the graph, then that's the same as lambda times the distance in hyperbolic space up to an additive constant. So this is actually a much stronger notion than if you're familiar with graph isometry, that kind of lets you take two different multiplicative constants and say you're allowed to actually stretch and contract distances by some bounded constant as well. Here we really just have one global scaling and then we just have an additive constant. So this is a really strong notion. And we also have that this map is approximately surjective, meaning if you take any point in gamma, then you can find a point U where the distance between the image of U is. So roughly the way you can think of this is it's saying that every Gromov hyperbolic graph bounded degree looks like a convex subset of in quite a strong way. Okay, cool. Moreover, for when you have an infinite transitive graph, you can always assume that gamma is equal to the convex hull of its ideal boundary points. Okay, so this is sometimes called, it's like gamma is visual or something like that. Okay, so so to give you an example of this, if I take a three-regular tree, then one way I can construct this set gamma is that I take a Cantor set in the boundary, right? So I go in the hyperbolic plane, and then let's say first I divide the boundary into 6 pieces like this and delete every other one, right? So I'm left with 3 pieces of the boundary, like here, here, and yeah, okay, here, and here, right? And then I keep iteratively deleting the middle third of each interval, right, until I'm left with this kind of Cantor-like subset of the circle, right? And then if I take the convex hull in the hyperbolic plane of this Cantor set on the circle, I get some set like what I've drawn in green here. So remember that geodesics in hyperbolic space are the same thing as arcs of circles which intersect the boundary orthogonally, okay, which is probably not exactly what I've drawn here, but that's what it's supposed to look like. Right? So basically, each time we get an interval in the that we delete from the Cantor set, we're going to draw this orthogonal circular arc over it, right, and delete that from our set, and then keep doing that. So we delete these 3 big ones, and then we get these three smaller ones on the next scale, and then a bunch of smaller ones on smaller scales and so on. Okay, and if you do this, what you'll see is that this set you can get, the convex hull of the Cantor set, is actually well, it's a convex subset of the hyperbolic plane, which you can identify with a 3 regular tree in this way. Right, so you see the blue tree I've drawn here. Again, the drawing is not perfect, but this is roughly how it goes, right? So first you have the 3 vertices corresponding to these 3 big boundary arcs that we deleted initially. Then each of those has 2 children going into the actually, I think I messed up this drawing. It's not really how it should look. Let's see if I can, let's try and do this. I think it should actually do this the first. So the vertices should correspond to the undeleted, the intervals that we don't delete at the first step, rather than the intervals we do delete at the first step. And then okay. Cool. And you obviously, you know, this map here is not uniquely defined because we do have this freedom to have this additive error. Okay. So the point of this for us is that even though we're working with these abstract Baron hyperbolic graphs, for many purposes, we can pretend we're in standard hyperbolic space. This can be quite convenient for lots of things, so we can really do some kind of explicit calculations with hyperbolic, which unfortunately I end up doing in the paper quite a lot. So one of the reasons I won't really be showing you a full proof of the main theorem here is just that it has a lot of parts of it which are just really inelegant and for messy trigonometric calculations and things like that. So I want to not do that, but to just get across some of the main ideas. So the proof is going to rely in a crucial way on this very cool theorem of Benjamini and Schramm, which, well, they call it a lemma, but I'm upgrading to a theorem. And this is from 2001, I think. And I should mention that although this result that I'm about to tell you about is due to Benjamini and Schramm, who are also the authors of the PC versus PU conjecture and lots of other work in population. The magic lemma actually comes from totally unrelated work about about local limits of random planar graphs. So in fact, it comes from the paper that led to the notion of Benjamini-Schramm convergence having its name attributed to them. Okay, so in that paper, what they were proving is that if you take any sequence of finite planar graphs of bounded degree, and you take any Benjamini-Schramm limit of that sequence, if the sequence Benjamini-Schramm converges to some random infinite planar graph, then that graph must be recurrent on the Schramm. And the way they did this is they looked at circle packings of planar graphs, and well, circle packing is a very cool thing that's not really related to what I'm talking about here. But basically, what it says is that if you have any planar graph, it always has a circle packing representation where you can draw the graph so that the vertices are circles and they don't overlap, and there's an edge between the two vertices if and only if the two circles are tangent to each other. Right? So circle packing theorem says that any planar graph can be any finite planar graph can be represented as a circle packing. So again, this isn't really relevant to what I'm talking about, but it's so cool. It's where this magic kind of came from. I just want to talk about it quickly. Right, so the circle packing theorem says that you can always represent finite planar graphs as a circle packing matrix. And Schramm, along with his co-author, he had proven like an infinite planar graph version of this, where in particular, moreover, this circle packing that you get, if the graph's a triangulation, then what you get is unique up to Mobius transformations and reflections. So obviously, if you apply a Mobius transformation or a reflection to the graph, this is actually the only freedom you have in choosing it preserves it gives you a new circle packing with the same constructs. So what Schramm and he had proven is that there's a similar thing. If you take a triangulation, an infinite triangulation of the plane, then you can always circle pack it either in the Euclidean plane or in the hyperbolic plane, but not both. If it has bounded degree, then this is equivalent to whether the graph is recurrent or transient. And so, which is a really cool theorem, and it's kind of like a discrete version of the uniformization theorem. Anyway, so Benjamini and Schramm, they wanted to prove that if you have a Benjamini-Schramm limit of bounded degree planar graphs, then it's recurrent. So by this Schramm theory of infinite circle packings, it sufficed for them to prove that any such limit always gets circle packed in the Euclidean plane rather than in the hyperbolic. Okay, so what they wanted to show is that if you take a sequence of finite planar graphs and you circle pack them all on the sphere, say, and then you're taking a Benjamini-Schramm limit, so you want to take this big finite graph and then just look at it locally around a typical point, right? So what they wanted to show is that take the circle packing, you look at it around a typical point, it looks like it's converging to a circle packing of the whole plane rather than to a circle packing of the hyperbolic. Okay, and the way they did this is by proving this general geometric fact about finite sets of points in Euclidean space, which is what's called the magic lemma. And let me first tell you the intuitive statement, because it's much easier to understand than the formal statement. So what it says is that from the perspective of a typical point in the set, any finite set of vertices in RD looks like it accumulates to at most 2 points of the RD union infinity, one of which is infinity. Okay, so of course, this looks like it's doing a lot of work here. So this is going to be the main thing to explain in the formal statement. Okay, so first of all, what do we mean by this thing from the perspective of a typical point? So the way we'll interpret this is that we'll look that each point has a kind of a characteristic scale associated to it and the set, which is what's called the isolation radius of the point. So this is just the minimum distance between, so if x is in A, the isolation radius is the minimum distance between x and another point of the set. Okay, and so this is this kind of characteristic scale of the point. We want to look at the set. We basically want to translate the set, if you like, so that the x is at the origin and the nearest other point is at distance 1. So what the magic lemma says is that for every epsilon positive and finite r, there exists a constant depending on epsilon r the dimension, and a set A prime, which has high density in A, so it has volume at least the volume of A times 1 minus epsilon. So that if you take any, so these are the kind of the good points. If you take any good point, x in A prime, then there exists a point y, so that the following holds. So if you take A and you look at all the points which belong to a large ball around x, so a ball of radius r times the isolation radius, and don't belong to this small ball around y, where this radius is the isolation radius divided by r, then the number of points in this set is bounded by this constant. Okay, and if it helps, think about it. If you fix epsilon d and let r grow larger, this constant is going to be growing roughly like r to the d log r. Okay, so it says basically, again, the intuitive explanation is that any finite set looks like it accumulates to at most 2 points, one of which is infinity. So what that's saying is that the set potentially has some dense region where there's a lot of points, but there can only be one dense region, so we cut it out. Okay? So if we cut out, there's some dense region we can cut out, so that if we also cut out the stuff that's far away, then we're left with a bounded number of points. Okay, and the point is this constant is universal, given the parameters epsilon, r, and d. It doesn't depend on the set A. Okay, and this thing about taking the subset with high density, you can think about this as saying something that if you take a uniform random point in A, then A will look kind of like this with high probability. It will have at most one dense region. So if you cut out the dense region, cut out what's far away, you're left with a bounded number of points. Okay, so for example, two kind of finite sets you might consider that have two different behaviors. So what's the simplest one perhaps is you just take a big box in a lattice, right? So if you do that, then typically if you take a typical point, it will be somewhere in the middle of the box, and what you'll see locally will just look like the infinite lattice. And this looks like it only accumulates to infinity. So if you take a big ball of radius r, it's going to have a squared twice, okay? Which is consistent with this. Another thing you might do is take some kind of exponential cylinder type thing. So if you take a large number of scales and then you put a constant number of points on each scale, then again, if you pick a point uniformly at random, it's going to be in like a middle scale with high probability, and what you'll see is something like this, where you'll have a large number of scales going down towards this convergence point, and also a large number of things going out towards infinity. And so if you take this big ball and you cut out this dense region here, then you're going to be left with actually quite a small number of points. Okay. Now, you might think, well, it's obvious that these examples have this behavior because they're kind of constructed. What if we try and construct a counterexample to the magic lemma? Well, one way you might try to construct a counterexample is something like this, right? So of course there are finite sets in RD that look like they're accumulating to lots of points from the perspective of some of their points, right? It's just that from a typical point, this won't be the case. So we try and construct an example here. Let's say we want to do this kind of dyadic approximation of the boundary of a square. So it's in the middle and then a bunch of points, and then we get closer and closer, we're getting more and more points, right? So from the perspective of the origin, this set, the sequence of sets, if you like, certainly looks like it's accumulating to the whole boundary of the square, right? But on the other hand, if you just do this to finite order and try and look at the set from a typical point, then, well, what will happen is that most of the volume of the set is in the boundary, is near the boundary, right? So, like half the set is right in this final layer, and then like a half of what's left is in the next layer, and so on. So if you pick a uniform point, it's going to be very close to the boundary of hyperbolic. So let's say we pick this one. And then if we do this thing where we look at the set from the perspective of that point, so we zoom in to the isolation of the radius of the point, what we see is something like this. And of course, this doesn't look like it's accumulating anywhere except to infinity. Okay. So what's really nice about the magic lemma is it says that you just cannot escape this behavior. No matter what finite set of points you use, you're going to see the same thing where from the perspective of a uniform random point with high probability, you look like you're accumulating to at most 2 points, one of which is an infinity. Okay, now, so as I said, I think my view is that the magic lemma is a really underrated, and beautiful piece of mathematics. Although it has this important role in Benjamini and Schramm's study of random and planar graphs and some subsequent work in the same area. So, in particular, quantitative versions of the magic lemma are important in the Gorogorovich and Anish resolution of the big conjecture that was around for a long time about the uniform infinite planar triangulations, which have unbounded degrees, so that they don't. This Benjamini Schramm proof doesn't apply to them, but the magic lemma remains really important in studying them as well. But outside this setting of random planar graphs, this hasn't been used very much. But I'm a huge fan of this theorem, and I found a few applications of this in some other contexts. So we'll see how we can use this in to study percolation on hyperbolic space, which probably at the moment you're thinking that it looks totally irrelevant to the study of percolation in hyperbolic space. So first of all, let's see a hyperbolic version of the magic lemma, which is actually just follows from the version of the hyperbolic, the Euclidean version, just by using the upper half space model of hyperbolic space and then just converting between the two things using trigonometry. So what it says, so first of all, we'll need a definition. So we'll call a set of points A in hyperbolic space delta separated if the distances between any two distinct points is at least delta. Okay, and so I think how distinct so badly. Okay, and but the point of this is we're not going to want things to degenerate down to the Euclidean case. We want to keep things really hyperbolic. So what the hyperbolic magic lemma says is that from the perspective of a typical point in any finite set, in any finite delta separated set, looks like it accumulates to at most 2 points of the ideal boundary. So maybe just to remind you what I mean by the ideal boundary. So, well, it's the same picture as before. So when we have the, say, the ball model of hyperbolic space, you know, this has two metrics on it. It has the hyperbolic metric, where as you get closer to the boundary, distances become larger and larger, and you can just go off to infinity and not converge to anything. But it does also have the Euclidean metric on it, right? And if you take the closure with respect to the Euclidean metric, you get you also get this boundary, which is just the unit sphere. Okay, and these are like possible directions that a geodesic and hyperbolic space can go off to. It's known as the ideal boundary. Okay, so again, how do we make this precise? Well, it's a similar thing. So take delta to be positive, and let A be a finite delta separated subset of hyperbolic space. Then for every epsilon positive and R finite, there exists a constant C depending on these four parameters: the dimension, the separation constant, the epsilon R, so that we get a set A prime of high density, such that if you have any X in the set A prime, again, we're thinking of A prime as the set of good vertices, good points, then there exist two half spaces, H1 and H2, which are both far away from X. They both have distance at least far from X, and that if I look at the number of points that belong to A, but not one of these two half spaces, then it's bounded by a constant. Okay, so of course, at this point you might be wondering, what is a half space, a hyperbolic space? Well, in 2 dimensions, it's really easy to say what it is. It's just, you know, you take your hyperbolic space, model as the disk, and you take a geodesic, and the two sides of it will be half spaces, right? Half space here, half space here. Okay. Of course, higher dimensions is similar, except instead of taking a geodesic to separate the two, you have to take a hyperplane. So like a copy of the d-1 dimensional hyperbolic space, the d-dimensional hyperbolic space. Okay. In particular, you know, if you take the sphere and then you cut it at the equator with a straight line going through the origin, that straight line, sorry, that plane, that hyperplane through the origin will intersect with the d-dimensional hyperbolic space to give you a d-1 dimensional one, and the two sides will be half spaces. Okay. So again, this is saying that most of the points of A, all but a bounded number of the points of A, are in these faraway half spaces, right? Which you can think of as open neighborhoods of boundary points. Okay.
Can I ask a question?
Yeah, please.
Can I ask a question? So in this statement, the same constants work for any A or A?
Yeah, right. Yeah, exactly. That's the whole point. So the same constant. So they depend on these parameters, right? Obviously.
Yeah. Mm-hmm.
But given the parameters, they work for any set A. That's kind of the whole point of what's going on. It's uniform.
Okay, thanks. Mm-hmm.
So, you know, often what the setting you'll apply this is that you'll have some sequence of sets A that you're interested in, something like that, as you get the whole same constant for the whole sequence. So some examples of what's going on here. So let's say I take A to be, okay, I mean, I've kind of drawn these like continuous sets in hyperbolic space for the illustration, but first of all, let's say we take, you know, all the points that belong to some hyperbolic lattice that lie inside a ball. Something like this, maybe, right? A really big ball. Then again, because what happens in hyperbolic space is that most of the volume of a big ball is near the boundary of the ball. like really near the boundary of the ball, like a constant distance away from the boundary. Okay, so if you take a uniform random point in this ball, it's going to be near the boundary with high probability. Okay, so if I look at the set from the perspective of that point, so remember in 2 dimensions, the isometries of the hyperbolic plane in this disk model are exactly the Mobius transformations that fix the boundary does and reflections. So maybe I picked my point. My uniform point is going to be somewhere here near the boundary. And if I apply a Mobius transformation to move that point into the origins, obviously I don't have to do this in the definitions, but just to make it easier to visualize, right? Then it's something like this, where now almost all the volume from the perspective of this point, almost all of the volume is near this point where you get near the boundary, right? So here in this example, it's actually sufficient to have just one half space. And the complement of that far away half space is going to have a bounded number of points. Okay. Now another example you might consider is this kind of tripod-like shape. And again, what happens here is that almost all of the mass of this tripod is kind of near the tips of this the shape. Okay, and but not really near the tip. So you'll still be basically what you see is something like a geodesic. So there's kind of like 1 point on every scale. Right. So if you pick a uniform point on the tripod, it's going to be deep in the tip, but still far away from the tip. So that if you, again, do the same thing where you Mobius transform that point to be at the origin to make it easy to visualize, then what you'll see is something like this, where the whole piece of this tip becomes something that looks like a geodesic, like a thickened geodesic, and it still is going to go off. The origin won't be right near the tip, so it will still go off in one direction, and then, but you'll be deep enough that you mostly just see this geodesic from this one point, and then somewhere really small over here, you see these other 2 pieces branching off, something like this. Okay, so that again, what you get as drawn here is that there are 2 distant half spaces here that contain almost all the points, almost all the volume of this set. Okay, and very roughly, what you can think of this hyperbolic magic lemma is saying is that these are the kind of the only 2 possible behaviors that when you take a big finite set in hyperbolic space that's delta separated, and you look at it from a uniform random point, then it has to either look roughly like a horrible, which is what happens in this example, or roughly like a geodesic, which is what happens in this example. Okay, and there are ways of making this precise, where you talk about the Benjamini Schramm limits of these finite subsets of hyperbolic space, and this is some kind of classification of the potential limits that you can get. So the limits will really converge to points in the ideal boundary that will either be 1 or 2. Right? And once you know which one it is, you can really learn a lot about this limiting object finite. So, we won't go into it. Okay. So this is a very nice thing about finite sets of points in hyperbolic space. I think it's a nice geometric fact. It still remains to be seen what the relevance of this is to percolation, right? So it turns out that the magic lemma, the hyperbolic magic lemma, is really useful in actually both steps of our strategy to prove PC less than P22. Right, so let's just review that strategy again. Right, so what we wanted to do is we had these 2 steps. The first one, we wanted to prove that the susceptibility blows up in the mean field way. And just to remind you, remember we saw before that it suffices to prove a differential inequality of this form, right? That the derivative of the susceptibility is at least a constant times its square. Okay, and then there was the second step that we wanted to take this big normalized matrix. Oh, yeah, there's a hand raised. Yeah, feel free to ask a question if you have one.
Yeah,
maybe you just
I had a small question before you move on. So in going from the Euclidean magic lemma to the hyperbolic magic lemma, I'm just wondering where does the delta separation come from? Like we had a isolation radius, right? We had an isolation radius, and we were trying to use it to find those big ball and small ball. But then you have a uniform analog of that in the hyperbolic case. Is that so?
Yeah. So the thing is that the isolation radius, you want to look at the Euclidean isolation radius. So yeah, where does it come from? That's a good question. Let's see if I can explain. So what we do is we use the upper half space model, and then we have these points, and let's just see. Okay, so you have this typical point, something like this, and you know that most of the points be either outside this big ball, which is something like that. All right, I think that's exactly the thing, that you want that when you scale by the isolation radius, that you still see the boundary of the space, basically. That's the point. You want to really, because what would happen, yeah, you want to say that when you take this big ball, in the big Euclidean ball around the points, that it's roughly the same thing as a half space. And that's because because of this delta separation. But if you take, it means that the Euclidean distance to the boundary of the hyperbolic space is of the same order as the isolation radius. So you still see the boundary of the hyperbolic space when you do this scaling. And then if you take a big enough ball, it will basically look like a half space. I don't know if that's it's something like you want to take this big Euclidean ball and then say, well, this is basically, doing the drawing here, this is basically the same thing as a half space.
Right.
Which isn't true if the points aren't separated. But yeah, a good question. Okay, so what I was saying, right, so we're going to use the magic lemma in both stages. So the first one, we want to prove this differential inequality, and then the second one, we want to study the norm of this normalized matrix. Okay? And roughly speaking, the magic lemma lets you prove something like what I was just saying earlier, which is that this thing where the matrix puts a lot of its mass near a single geodesic is kind of the only obstruction to having that small. Okay, we'll see how you can prove something like that using magic lemma. So let's first discuss this first step. And as I said, well, this one's not too bad, but in part B, things actually get really technical to do it properly. So I want to keep things a bit vague and give you the main ideas. And if anything's not clear, please don't hesitate to ask. Okay, so we want to do this first step of proving that the susceptibility blows up at most like 1 over epsilon as you approach PC from below. And as before, it suffices to prove this differential inequality. Right? And also remember that we saw that the derivative of the susceptibility we can express in basically this way, where you take an edge and you look at the expected product of the volumes of the clusters on either side of the edge times the indicator that these two clusters are distinct. Okay. Now, one thing that's often useful is that by a small argument, you can get that it's sometimes convenient, instead of having just an edge, like having these 2 points be next to each other, you can take them to be distance 10 or something like that. So you can prove by a kind of surgery argument, quite similar to ones we discussed last lecture, that this is the same order as if you take 2 points x and y, which are not necessarily neighbors, provided that their distance is bounded by a constant, right? Where the constants that you use to compare these two quantities are going to depend on this distance. So how are we going to use the magic lemma? Well, first of all, so for this step A, we're actually not going to use the full power of the magic lemma. We're just going to use a consequence that it has, which is actually something you can prove directly and was known for this magic lemma stuff. So here's the consequence. Suppose I'm in at least two-dimensional hyperbolic space, and I have one of these delta-separated sets A. Okay? Then there exists a set A prime. Again, you can do this with the epsilons and stuff, but let's just say that it has at least half the volume of A, such that if X belongs to A, then there exists a half space H with, there exists this constant R. So this half space is not too far from the point X and is disjoint from A. Okay, so this is kind of quite a different, before the half spaces we were discussing before, like these ones here, which have most of the volume of A. Here we're getting a half space that does the opposite thing, it's disjoint from A. Okay. Now, why is that true? Well, we know that we have these two half spaces where most of the volume of A lies, right? All but a constant amount of the volume of A lies in these half spaces. So there's almost constantly many points in this complementary set. And of course, if R is large enough, I can take like a bunch of disjoint half spaces like this, right? And they can't, and at least one of them has to not intersect A if there's enough of them, because A has like a constant number of points inside this grid. Okay. So moreover, I won't go into exactly why this is, but
sorry, but did you mean A prime intersects H trivially?
No, I really mean A intersects H trivially. So in the magic lemma, we take this set A prime, but this is like the set of good base points, if you like, and then the actual statement that you get is about the whole set A.
Okay,
So
X is chosen from A prime. Okay.
Right, so X is in A prime. You look at it from the perspective of one of these good points, but you really look at the whole set. You don't throw away the extra points. Okay, good. Right, and so I won't go into exactly why this is true, but so there's something that's a bit unsatisfactory about the statement that I've just told you. So we're going to want to apply these statements to sets of vertices, right, where we've taken our Gromov hyperbolic graph and we've mapped it into the hyperbolic space using the Bonk-Tan theorem. And of course, what might happen there is that this embedding, it only gives you some convex subset of hyperbolic space, not the whole space. And maybe this disjoint half space that we found here is just trivially disjoint because it doesn't contain any vertices of the graph. So in fact, you can get this, you can improve this statement to say, and this is not obvious, but it can be done, that when you have a non-amenable hyperbolic graph that you're embedding into this space using Schramm, then you can really take this disjoint half space to be a half space that's not trivially disjoint, so that it really has a good intersection with the set gamma. In particular, the set gamma is going to accumulate to some boundary point that's in the interiors of the. Okay. Basically,
So you
what
wrote X is
happens?
in A. You should write X is in A prime, right? I mean, you have written
yeah.
X is in
Oh,
A.
yes. Sorry. Thank you. Okay. Basically, the reason why this is true is that you can prove by contradiction that if you couldn't find this half space, then actually G would be amenable, because the obstruction to being able to find this half space that's both disjoint from the set A and is actually has a good intersection with the set gamma. The obstruction to that would be that like the graph actually just looks like a line near this point X, which would be anyway. This is some additional. Basically, we can get some additional non-degeneracy conditions on these half spaces if we want to. Now, what's the interpretation of this? Well, the best way to think about this is that, well, in the non-amenable graphs are characterized by the property that if you take any finite set of points in the graph, then most of the points lie near the boundary of the finite set. Okay, that's kind of the definition of non-amenability. Because non-amenability is usually stated just as the constant fraction of the points are in the boundary of the set. But in fact, it implies that a high fraction of the points are within distance A of the induction. So what this lemma says is that hyperbolic non-amenable graphs have a stronger property, which is that if you take any finite set, then not only is most of the volume of that set near the boundary of the set, but in fact, most of the volume of the set is near the boundary of the convex hull of the set. Okay? Because, well, being in the boundary of the convex hull is exactly having this by kind of supporting hyperplane type thing, right? That if you have a convex hull is like the what you get when you throw away every disjoint, every half space which is disjoint from your set. So right, so this having this nearby half space which is disjoint from your set is exactly saying that you're near the boundary of the convex hull of the set. But again, this is actually something that was known before, and although you can prove it using the magic lemma, it's not really using the full. Okay, now why is this relevant to percolation? Well, when you have unimodular graphs, the mass transport principle roughly tells you that the origin is uniformly distributed on its cluster. Now, of course, that doesn't literally make sense because the origin is not random. But it means that if you look at any statistic of the cluster, then the expected value of that statistic at the origin will be equal to the expectation of the average of that statistic over the cluster at the origin. That's something you just directly get from the mass transport. So in particular, one instance of this is that if you have any statement like the magic lemma, which tells you something about finite sets viewed from a uniform random point having some property with high probability, then the mass transport principle tells you that if you have if you take the cluster at the origin, then the origin will satisfy this property with high probability. So in particular, if you condition on the volume of the cluster at the origin, then what you get from this is that with high probability, so there's some constant r, such that, say, with probability at least of half, given that the cluster is large, you nevertheless have some half space, which is distance at most r from you, so it's not too far away, and it's disjoint from your cluster. Okay? again, this is just because a typical point in the cluster of the origin will have this property, therefore the origin has this property, this probability. Okay. Now, what you can do then is you can do a kind of a compactness argument to, so here the location of this half space is random. But using a small compactness argument, which I won't go into, you can change the order of the quantifiers so that you can find like one particular half space that's not too far away, which works with good probability. Okay, so in particular, what you can show is that, and it might depend on P, but that's not really a problem. So there exists a half space spanning across P and P with distance at most r from the origin, so that if you take basically the conditional on the size of the cluster at the origin, you still have a reasonable probability not to intersect this half space roughly. The precise thing you get is that if you take the expected volume of the cluster at the origin on the indicator that you don't intersect this half space, then it's of the same order as just the normal susceptibility. Okay. And again, as I've written it, this is maybe trivial if your graph really lives inside some non-trivial convex subset, because you could just take H to be disjoint from the whole graph. So that's not common to do. But again, with a bit of work, you can make sure that this half space is really chosen in a non-degenerate way. So you have a good amount of your graph really inside this. Okay, so once you've shown this, it's actually easy to conclude step A. So how do you do it? Just erase one. Of course, a different way you could phrase this is that if you looked at the complementary half space, then this would be a half space that actually contains the cluster and has boundary close to S. Close to S. So I could find a half space that where I do this the other way around, where I get the. If I have a half space whose boundary is not too far away from the points, but conditioning the cluster to be contained in this half space doesn't change its expected volume by too much, right? This is just again just taking the complementary half space compared with how I phrased it before. Okay, so what you can do is you can take 2 points x and y, where the distance between these 2 points is like 2r or something like that. Okay, and you can set it up so that these points x and y, they each have their own half space associated to them, hx and hy, so that the boundary of these half spaces is at most this constant distance away from x and y respectively, and that if you condition the cluster of x to remain inside its half space and the cluster of y to remain inside its half space, then it doesn't change the susceptibility by too much, just by a constant. Okay, but this of course implies that the expected product of the volumes, given that x and y are not connected, is a constant times the square. And why is that? Well, if I condition this cluster to stay inside this half space and this cluster to stay inside this half space, then they become independent, right? Because these half spaces, they don't have anything to do with each other, they don't share any edges. So, so given this conditioning, the two clusters become independent, and then I just used these estimates here. Okay, so you get that these 2 points, that exactly what I just said. So the the expectation of the product of volume of the two clusters, given the clusters are different, i.e. x and y are not connected to each other, is at least constant in the square of the susceptibility. Okay, and as I said before, this quantity, because x and y are a bounded distance away from each other, you can say that this is actually up to constants the same thing as the derivative of the susceptibility, and then this completes the proof of this mean field behavior. Okay, so that completes the first step A of our strategy. So, so in the remaining 10 minutes, let me just try and sketch roughly how step B is going to go. Okay, so what did we need to do to prove step B? We needed to prove that this, if I take the normalized matrix, which I'm making to a bistochastic matrix, then its norm is going to 0 as P goes to PC. Okay. And of course, the nice thing about this being a bistochastic matrix is that as probabilists, well, we're used to dealing with transition matrices of random walks, and we know various tools and techniques for estimating things about them. In particular, what we'll use is something called Cheeger's inequality, which relates the norm of a, so this is something that's usually stated for transition matrices of simple random walks on graphs or something like that, but it's actually true for any symmetric bistochastic matrix. Okay, so for any such matrix, you can define its Cheeger constant in a totally analogous way to how we defined it for graphs before. So this actually gives you the same thing as we had before if the graphs are regular, which is what you need for the bistochastic. So you define H of P for a bistochastic matrix, a symmetric bistochastic matrix P, to be the infimum where over finite sets of vertices, where you sum over U in the set, V not in the set, PUV divided by the volume of V. So you should think of this numerator here as being like the size of the boundary like we had before, but now it's measured with this matrix P. Okay. And Cheeger's inequality, which has a long and storied history, as you can see here. So Cheeger really proved some version of this for in the differential geometry context, like a continuous version of this. And there's various generalizations due to various people. But in any case, what this says is that you can bound the operator norm of P in terms of the Cheeger constant, okay, with these explicit bounds, but the important thing for us is that this norm being small, close to 0, is equivalent to the Cheeger constant being close to 1. Okay. And indeed, if we want to prove this step B, then it suffices by this inequality to prove that, so if you look at 1 minus H, 1 minus the Cheeger constant of the normalized matrix, then it's the same thing as the supremum. We want to show that this is small when P is close to PC. Okay, so the supremum, I'm summing over, so because I've done 1 minus, I get sums over pairs that both belong to W instead of 1 in 1 out. Then I get sum over pairs both belonging to W of the connection probabilities divided by the size of W times the susceptibility. Okay, and the thing which makes this nice and makes the magic lemma relevant is because I have this thing here, the sum over pairs of points in W, and I'm dividing by the size of W, I can interpret this as saying something about the set W viewed from a uniform random point, right? Because I'm summing over this first coordinate U and then dividing by the number of vertices. And so we know that if we, by the magic lemma, that if we take any finite set W, big finite set W in a hyperbolic graph, what it's going to look like is that you have all but a constant number, from a uniform point, all but a constant number of the points in that set are going to be in at most 2 distant path spaces. Okay, So what that means is if we want to show that this is small, we can split this sum up into two pieces. We can get the piece that comes from, well, the piece that comes from U being one of the bad vertices that the magic climber doesn't tell us about. And this is just small because, you know, it's epsilon, right? We can make it whatever we want. And so that first piece is dealt with. So we can ignore that. Now we only need to look at the case where U is one of these points, one of the good points that the magic climber is telling us about. Okay. Now, once you do that, the remaining points, the points V that you're summing over, there's kind of two kinds of points, right? There's the ones that are in these distant half spaces, and then there's the ones that aren't, right? But there's only a bounded number of the latter kind of points, and we're dividing through by the susceptibility, which is going to infinity. So that set the close points, the ones that aren't in these distant half spaces, is again just negligible. The contribution from them goes to zero. Okay, so the only thing that remains to look at are these points which belong to these distant half spaces, right? And there could be a lot of those points. Okay, but in order to bound the contribution from those points, well, we can upper bound it by the contribution, the sum over the entire half space. So if we can show that if you sum the connection probabilities from the origin to the whole of a faraway half space, if we can just show that that is small, so we just need to show that it's smaller than the total susceptibility by a factor epsilon, which is going to zero as the half space gets further away, then we're done, right? Because again, there's kind of three things we're splitting up to: the points that we don't get, the U's that we don't get control of from the magic climber, which we can take to be negligible; the close points, the points that aren't in these faraway half spaces in the magic climber, there's a bounded number of, that's negligible because we're dividing through by something big. And then finally, the points that are in these faraway half spaces, which will be dealt with if we can prove this. Okay, and I don't have very long to say much about this. Actually, it's quite technical, but let me just say it briefly. So first of all, by the BK inequality, if I want to connect to some point in the half space, well, I have to first connect to some point in the boundary of the half space and then get to that point. Okay, where you have to interpret the boundary in the right way so that it's really like a vertex boundary you have to go through to get from one side to the other. Okay, so if you do that and you do the sum, you see that the expected number of points you connect to inside the half space is at most the expected number of points you connect to in the boundary of the half space multiplied by the susceptibility. Okay, so we just need to show that if the half space is far away, then this expected number of points we connect to in the boundary of the half space is small. It is some function of the distance. Okay, and this is still a tricky thing, but the idea basically, so you know, one thing with percolation, it's always hard to get started and just prove some non-trivial estimate about, say, critical percolation, because a priori you have almost nothing to work with. So what we can use here is a nice observation that one situation which you can control the sum of the 2-point function over a set is if you're in a Cayley graph and you have a set of group elements which generate a free semigroup. So in other words, if you look at all sequence products of finite sequences of the elements of A, then different sequences give you different products. Okay, that's what I mean by generating a free semigroup. And there's a nice observation, which is that if you have any set of points that generate a free semigroup, and you sum the connection probabilities from the identity to these points, and you're below criticality, you always get at most one. And why is that? Well, it's basically if you look at the sum of the connection probabilities over the whole semigroup that you generate, right? Well, because all the different sequences give you different points, you can express this as a sum over sequences like this. And then, by FKG, you can write this as it's at least this geometric series where you're summing over the sum just of the elements of A to the power of n, summing over all that. Okay, when you're below PC, this is at most the susceptibility, so it's finite. So this quantity must be strictly less than 1. And then it must still be less than 1 at PC by the usual left continuity test. Okay, so this is one setting where we can get a bound on these sums kind of for free. Okay, and the problem is, well, first of all, if I take the boundary of a half space, but it turns out this isn't one of these free things necessarily, but it's very close to being one. So it turns out you can always take a kind of a net for this set, which does have this property that it generates a free scenario. There's versions of this that work. Okay, so in other words, if you have this boundary of a half space, you can find some other set A so that the boundary is contained in a constant size neighborhood way, and A does have this free property. Okay, and given that, you can show that the expected number of points you connect to, it's hard to say to one of these boundaries of a half spaces is at most a constant, because you can relate it to the sum over the set A, which is in there. Okay. Now, of course, this isn't good enough because we wanted to show that it's bounded by a small constant. Okay. But you can fix this. Basically, what you do is you stack a bunch of hyperplanes on top of each other, and you say that this stack of hyperplanes has the same property, that it's approximately free. And then the sum over all the hyperplanes has to be at most constant, so there must be one of them where it's small. That's how you conclude. So I'm already over time, so I'll stop there, and I'm happy to answer any questions.
Thank you, Tom, for this wonderful talk today. Are there any questions for Tom?
Yeah, I had one. Can I?
Go ahead.
Oh, okay.
Go ahead. Yeah. Oh, sorry.
Yes. Okay. Do you have an analog of magic lemma for groups, for hyperbolic groups? For free groups?
Yeah, indeed. So, well, I should say, first of all, for free groups, it turns out that the way you prove the magic lemma is you actually start by proving something for trees, and then you deduce the real case via some kind of dyadic encoding. So the free group version is kind of more primitive. But for hyperbolic groups, you can deduce a version of the magic lemma from this one by using the Schramm theorem. So you can embed the group inside the standard hyperbolic space and then just by this.
But there is no version of Schramm for groups.
For hyperbolic groups.
For hyperbolic group, only for graphs.
Oh, sorry, I see what you mean. So you mean like?
So I have an abstract.
I mean, it's like a metric notion, right? It's
right. Yes.
I don't know how you would formulate it without a specific metric on your group.
I have word metric. Yes.
Yeah. Right. Right. Yeah. But the group with the word metric is a hyperbolic graph, and then you can apply.
I can define convex half as you did in the Kelly graph.
Yeah. So I should say that you can Schramm embed into standard hyperbolic space and apply the magic lemma. And if you pull that back, you can get like an intrinsic formulation of the magic lemma for the graph, which doesn't refer to the embedding. You have to define what this notion of a half space is. It's basically, it's the kind of set that gets mapped to a half space under one of these embeddings, if you like. But you can define that as well, and then you get an intrinsic definition of an intrinsic version of the magic lemma for hyperbolic groups.
Thank you.
So, okay, I guess Ritik was,
Yeah. Yeah, I had a small clarification. So this was the part where you took 2 points x and y in the Poincare disk and then separated them using two. Yeah, exactly. Yeah. So yeah, we use these two inequalities to establish the this differential inequality. So the inequality that we have here, is this really just a strengthening of this inequality that you had said was there in the Eisenman paper for the Euclidean lattice? I mean, there they had a rectangle and then they were separating two clusters using an edge. And here you have strengthened it to the hyperbolic.
No, it's they're quite different actually. I mean, these two inequalities kind of go in opposite directions. Yeah, I mean they're related, but somehow the Eisenman-Cassel-Newman thing is like a general thing, but it's like an upper bound on the probability you have these two big clusters near each other. Whereas we're actually doing the other thing, we're proving a lower bound on having two big clusters near each other.
Oh, right. Yeah, sorry. Yeah.
Are there any further questions for Tom? If not, let us all give a big hand to Tom for giving this wonderful series of lectures.